Good morning, students. Hey, before we get started today, I just thought we'd begin to do warm-up problems every day. So here are 4 problems for you to do. Number 4 is actually kind of a problem that we've not done before, so see how you do on that. If you want to pause it right now, work through these, and then hit play again, I'm going to start to work them now. All right, so we'll take the first one, and I'm just going to move over to the next page here. All right, here's our original problem. If you take a look at the sequence definitely goes to 0. When I Lopatize that is bottom heavy, it's going to go to 0. I'm not going to show you that to save a little time. The plus 1, the root n on the top, and the n squared on the bottom tells me that it's super close to a p-series, just not quite close enough. So that means if it's close to a p-series, I'm going to compare it to what it boils down to, which is the sum from 1 to infinity of 1 over n to the 3 halves. That is n to the 1 half on the top, n squared on the bottom. That is 4 halves on the bottom. Subtract them. 1 over n to the 3 halves. I know for a fact that 1 over n to the 3 halves is a convergent p-series test. Then using the limit comparison test, I want to take the square root of n all over n squared plus 1. I'm going to put that over 1 over n to the 3 halves. I want to take the limit as n goes to infinity. I copy dot flop. That's going to give me n squared all over n squared plus 1. Taking the limit of that, using L'Hopital's rule, that gives me 1. Again, I'm not showing the L'Hopital's rule. I would like you to on a test or a quiz. So please do as I say and not as I do. Now, check this out. This is finite and positive, which means that my original problem does what I'm limit comparing it to. So that means that my original problem converges by the limit comparison test. All right. All right, here's the second problem. If you use the root test on this and you take it to the nth root, what you're going to get is n plus 1 over n, which L'Hopitizes to 1, which means if I'm using the root test, it's inconclusive, so I can't use the root test. Remember, a result of 1 tells you nothing. All right, so here's what I'm going to do. I take a look at the sequence, and if I drive n to infinity, what I get is 1-ish to infinity, and that is indeterminate. So I think I need to know what the sequence does, which may indeed tell me what the series does. So let's examine this. If I set y equal to n plus 1 all over n to the n. I want to find out what this does. I want to get this exponent down to the front, which means I want to natural log both sides. That's going to give me, if I go over here, the natural log of y on the left, and I've got n times the natural log of all of that stuff in there, n plus 1 over n. Now what I'm going to do is I'm going to take this n, and I'm going to move it to the bottom. And then I'm going to take the limit as n goes to infinity. Now, that gives me the natural log of 1 on the top, which is 0, all over 1 over huge on the bottom, which is 0, still indeterminate, but now I can L'Hopitize it. So I'm going to go over here now. I've got the natural log of y on the left-hand side. If I L'Hopitize the top, what I'm going to get is 1 over this, or just that flipped, n over n plus 1, times the derivative of that function, which gives me n times 1 minus n plus 1 all over n squared over the derivative of the bottom, which is negative 1 over n squared. So now what I want to do is just clean this up. I've got the natural log of y. This is equal to, this portion right here just gives me negative 1. And if I copy dot flop with the bottom, everyone stick with me here, that's going to give me positive n cubed on the top. And on the bottom, what I'm going to get is n cubed plus n squared. Now, if I L'Hopitize that, what I get is 1. And then I bring the e over to the other side. I get y is equal to e to the first. Which means my sequence does not go to 0. So my conclusion is my original problem diverges by the nth term test. I'd like it to be a little bit more organized than what I've got here. But again, we're doing as I say and not as I do. All right. All right, so the third problem, as you can see, I've already written out the first through sixth derivatives for the cosine of x, and that's necessary if I'm coming up with a Maclaurin polynomial estimation of the cosine of x. So now I'm going to take these values in this column right here, and I'm going to use that as my numerator for each one of the terms of my sequence. So if you recall the formula, I'm going to get 1 over 0 factorial, that's x to the 0. The next one is 0, so this is minus 1 all over 2 factorial x squared. That's going to be plus 1 over 4 factorial x to the 4th, and then minus 1 over 6 factorial x to the 6th. So this is p sub 6 of x. If I clean this up, p sub 6 of x then turns out to be 1 minus 1/2 x squared plus 1/24 x to the 4th minus 1 over 720 x to the 6th. Now, if I'm looking for the cosine of 1, that's f of 1 is equal to the cosine of 1, which is going to be roughly equal to or approximated by p sub 6 of 1. What I'm going to do is take 1 and plug it into my p sub 6 line. So p sub 6 of 1 is equal to 1 minus 1/2 plus 1/24 minus 1/720, which gives me something like 0.5403 if I go to 4 decimal places. So the question is, hey, how close is that to the actual value of the cosine of 1? Well, the tie-in is this. If you take a look at this polynomial estimation of the cosine of x, what you get is an alternating series. And alternating series remainders, which is what we are looking for, what I'm looking for here is r sub 6 of 1. That is going to be less than or equal to the first neglected term. Now, if I just go to the very next term based on this approximation here, it's a 0 term. So I've got to skip that because obviously if I'm only using the first 4 terms of this polynomial estimation, I am definitely not exactly at the cosine of 1. So remember, this is also absolute valued. So my r sub 6 of x is going to be less than or equal to 1 over 8 factorial times 1 to the 8th. So that's the answer to number 4. This is my remainder for a 6-degree polynomial estimation of the cosine of 1. Now, it's not Friday, but I know last Friday I didn't give you a fascinating fact, but I actually did this on a graphing calculator. And if I actually take p sub 6 of 1 minus the cosine of 1, what I get is, so the actual is 2.453, I'll go to 3 decimal places, times 10 to the negative 5th. And my r sub 6 of 1 is less than or equal to 2.4802 times 10 to the negative 5th. So again, remember that this gives you a high side difference or a high side estimation between the partial sum and the actual sum, and that's pretty close. You'll note that this is just slightly bigger than that, so there's some wiggle room there. But this would be the answer that I'm looking for. And yes, fascinating. All right. So let's start the lesson for today. This is 8.8. This is power series. It's part 2, and what we're going to do is we're going to derive. And integrate them. Okay, let's start off with the theorem. What the theorem says is something like this. If f of x is equal to the infinite sum from n equals 0 to infinity of a sub n times x minus c to the n. And again, that is a power series. It's got x's and c's in it. With an interval of convergence of c minus r to c plus r, and I should mention that r equals the radius of convergence. That is the distance between where it's centered and the outermost possible value of x values, which will make the original power series converge. And what you'll notice here is that I've got parentheses on here right now. Then the following is true. If I take the derivative then of f of x, and you'll notice that this original f of x is my power series. In order to derive that, what I do is I take then the sum from n equals 1 to infinity. And I should mention this, whenever you derive a power series, this index increases by 1. So I start off with my original power series starting at 0. When I derive it, it increases to 1. And that then gives me a sub n. And then what I do is, what I'm doing is I'm deriving with respect to x. So I only focus on the portion that has an x in it. And I'm going to derive it just like I did back in chapter 2. I'm going to bring the n down to the front. I leave the innards the way they are, x minus c, and then I take 1 away from the power. Technically, if I'm using the chain rule, I got to multiply this by 1, which is the derivative of my x inside of here. So it's fairly easy to do. Again, you take the portion that has an x in it, this portion right here, take the n down to the front, and then take 1 away from the power. When you integrate, the integral of f of x dx is equally as easy. Now, when you integrate, the lower index stays the same. So this is the sum from n equals 0 to infinity. And what I get is a sub n. And this will be then x minus c to the n plus 1, that's power plus 1, all over power plus 1, plus c at the end, because we're integrating. And again, the assumption here is that I've used u substitution. So my u is x minus c, du is equal to dx. So I'm really integrating u to the n. So it's power plus 1 over power plus 1. As opposed to derivatives, which is power down to the front, take 1 away from the power. All right, let's work through a few problems. I guess I should add something here. Let me get rid of this, make a little room. And I want to add this. The interval of convergence is the same for all three, except possibly at the endpoints. You gotta check them. So it's just like we were looking for the interval of convergence. Remember, you got an overall interval of convergence, and then I had to take that additional step of checking each one of the endpoints to make sure, or to determine rather, what happens actually at the endpoints. The same thing happens here. Whenever you derive or integrate a power series, you've got to check the endpoints into that either derived or integrated expression. And I should add, I've got in red here that the interval of convergence is the same for all three. Again, it doesn't matter how many times you derive or integrate it, you will still have the same overall interval of convergence. All right, I'm just going to work through a few examples and then cut you guys loose. So the way this works is they will start you with a problem like this. They will tell you what f of x is. In this case, it's the sum from 1 to infinity, negative 1 to the n plus 1, x minus 1 to the n all over n. And again, just like originally or earlier in 8.8, this is a power series, so you know this is going to converge somewhere. Your task in this section is, again, to find the interval of convergence. Not the radius, but the actual interval. So they will give you this original function, and they will ask you to find the interval of convergence for f prime prime of x, and the integral of f of x dx. Now, the nice thing about this is you only need to find the overall interval of convergence once, and then you can just test the endpoints into the derivative, the second derivative, and the integral. You don't need to go through the ratio test 4 times. So let's go ahead and test the interval of convergence on the original. Let's just use this and find out where it actually converges. So again, we use the ratio test. I take the limit as n goes to infinity of what I get is x minus 1 to the n plus 1 all over n plus 1 times the flip of the original, which is n, over x minus 1 to the n. Absolute valued less than 1, because I know it converges. I'm just looking for where it actually converges at. All right, so if I go ahead and reduce this, remember, the limit of a product is equal to the product of the limits. So really, what I can do is, first of all, cancel the x minus 1 to the n. I've got one more x minus 1 on the top than I do on the bottom. And then using L'Hopital's rule, n over n plus 1 gives you n. And again, I'm not showing that, but I'd like you to show me that. All right, get rid of this. All right, good. So I know that x minus 1 then is less than 1. Using a little algebra, x minus 1 less than 1, x minus 1 greater than negative 1. That means x is less than 2, x is greater than 0. By the way, going from 0 to 2, the question is, what do the endpoints do? If you look at this original power series, this thing is centered at 1. C is equal to 1, and 0 and 2 are equidistant from 1. So I know I'm on the right track. All right, so let me make a little bit of room here. Get rid of this. We'll get back to this. All we have to do then is use that overall interval of convergence right here, 0 to 2, and find out what happens in the derivative and the integral. Okay, so on to the next page, just to give myself a little room. This is the original problem here, and again, what I'm looking for is the interval of convergence for f prime, f double prime, and the integral. So to find f prime of x, what I'm going to do is take this. This is the sum then of n equals 2 to infinity, of negative 1 to the n plus 1. Now what I do is I am only deriving the portion with an x in it. So the n comes down to the front. Let's try that again. N comes down to the front. X minus 1 to the n minus 1. This is all over my original n. Now you can clean these up before you actually test them. So these n's do cancel. And then all I'm doing is testing. I'm testing then the simplified version. So let's test each one of these individually. I'm going to test 0 first. I take this derived version and I plug in 0. This gives me the sum from n equals 2 to infinity. That looks horrible. Let's get rid of that. And let's try that again. All right, good. This is negative 1 to the n plus 1. This is negative 1 to the n minus 1, which simplifies to the sum from n equals 2 to infinity of negative 1 to the 2n, which is the same as the sum from 2 to infinity of 1 to the n. This diverges by the nth term test since the sequence does not go to 0. So that means for my derivative, I have a lower bound of 0, not including 0. All right, let's do it again and test at 2, and I think you can already see what's going to happen. I've got the sum from n equals 2 to infinity. I just noticed something here. This actually was 0. So these should be 1s. Nice thing about it is it doesn't change the way you work the problem. Okay, I plug in 2. I get negative 1 then to the n plus 1. That's going to be 1 to the n minus 1. Now, as opposed to the warm-up, this is actually the number 1 to the n minus 1, so that's gone. This then turns out to be the sum from n equals 1 to infinity of negative 1 to the n plus 1. This is an alternating series. So I take the limit as n goes to infinity of 1. That is not equal to 0, so that diverges by the alternating series test, which means at 2, it's not included either. So my interval of convergence for f prime goes from 0 to 2. All right, here's my original f of x. Got that written down correctly. Yep, and then I'm going to integrate, because I think the second derivative is actually just as easy to see as the first derivative. But if I integrate this then, the integral of f of x dx, I know I'm going to go from 0 to 2 because, again, they all have the same overall interval of convergence. I just have to check the endpoints. And so now I'm going to integrate f of x dx. So here's what I got. I got the sum from n equals 0 to infinity, negative 1 to the n plus 1. That part stays the same because it doesn't have an x in it. I integrate x minus 1 to the n. That gives me x minus 1 to the n plus 1 all over n plus 1 times the n that was originally down there, plus c. Okay, now I'm going to test my two endpoints. So I'll test at 0 first, and again, I'm going to plug it into my integral here. So I've got the sum from n equals 0 to infinity. I've got negative 1 to the n plus 1. This is going to be negative 1 to the n plus 1 all over n times n plus 1, which simplifies to the sum of negative 1 to the 2n plus 2 all over n times n plus 1. The top just goes to 1, which is the sum of 1 all over n squared plus n. If I clean up the bottom, and what I'm going to do is I'm going to limit compare that to the sum of 1 over n squared, which is a convergent p-series test. If I do 1 over n squared plus n over 1 over n squared, and I copy dot flop, I take the limit as n goes to infinity of n squared all over n squared plus n. That's going to L'Hopital's to 1, which is positive and finite, which means that at x equals 0, it converges by the limit comparison test. So I know now that the left-hand side, get rid of this, 0 is included. All right, let's test the other side. Just making some room here, that is the integral of f of x dx. So it's power plus 1 over power plus 1. And now all I got to do is check the other endpoint. That's at x equals 2. So I'll take my power series and I plug in 2 for x. This is 0 to infinity. Negative 1 to the n plus 1. This is going to be 1 to the n plus 1 all over n times n plus 1. I've got the c out there, but it doesn't impact convergence or divergence. It's just a single term. So what this then simplifies to is the sum from n equals 0 to infinity of negative 1 to the n plus 1 all over n squared plus n, because this right here actually is 1. And what I have here is an alternating series. So what I'm going to do is I'll do step number 1. I'll take the limit as n goes to infinity. And remember, you use just the portion that does not alternate. That's 1 over n squared plus n. That is equal to 0. Check. Step 2, 1 over n plus 1 squared plus n plus 1 less than or equal to 1 over n squared plus n. Check, because I told you it's true. So this converges by the alternating series test, which means my overall interval of convergence goes from 0 to 2, including the endpoints. So as you can see from those just two examples, either deriving or integrating, you do get different results at the endpoints. So you've got to make sure that you check them. All right, guys, thanks for hanging in. I appreciate you guys continuing with this process. Hopefully it's helpful. Please let me know what you're having trouble with, and I'll get you all squared away on the next video conference. Thanks.